Hi, today we're going to be looking at filter design. And so first we're going to be designing a single stage low pass RL filter using a 100 millihenry inductor, and we're going to try and get the cutoff frequency to be a specified amount. And then we're going to do the same thing with an RC filter. Then we're going to have some fun and explore around adding them together and see what we get. I mean, the first part's going to be fun too, but we're going to have even more fun in the second part. Yeah, so let's give this a shot. Single stage RL low pass filter. So here's just some components we can move around. So here's our 100 millihenry inductor. We're going to need that thing. Maybe we'll put a voltage supply there, and we'll get a ground. And if we want it to be a low pass filter, keeping in mind that the inductor is a short at low frequency, then a single stage low pass filter will look something like this. So it still would be a low pass filter if we put in extra resistors in here, but if we just want to make it simple and have the maximum gain, then we'd build it something like this. Now this will not necessarily have the right cutoff frequency that we want. It does have the right inductance, but we need to choose this resistance. So the only design parameter that we have is the resistance. So with this in mind, the transfer function of the low pass filter is going to be something that we can determine from this. So I'm just using a clipping program to take a picture of that, put it in here. Need to choose the R value for this circuit. Okay, so transfer function is going to be just keeping everything in variables. H is equal to, from a voltage divider, R over j omega L plus R, which means that the magnitude of H is going to be equal to 1 over root 1 plus omega L over R squared, and 3 dB frequency is when omega L over R equals plus or minus 1. We're only going to have one value of this for a positive omega, so this tells you that omega 3 dB, I guess maybe negative 3 dB to be a little bit more clear there. The minus 3 dB frequency should be equal to R over L. All right. Okay, so that means that if we have if we want a cutoff frequency of 15 kilohertz, omega is equal to 2 pi f. So that allows us to solve for what R should be. In this case, we're doing a design problem where we need to pick what the R is. So R is equal to omega L, which equals 2 pi f times L. So that would equal 2 pi 15 kilohertz times 0.1 henries, and that ends up being 2 times 3.14159 times 1583 times 0.1. We'll get 9425 ohms. Okay, so there we go. There's our resistance, and if we like, we can check that out in multisim. So even if you can't get a resistor that has exactly this very easily, 9425, yeah, 9425, then you could imagine combining different resistors in a clever way until you get exactly the resistance that you need. So now there's our 9425, and we can add in a Bode plotter tool just to check out whether or not this is working the way that we think. Let's see. All right. So indeed, we've got our low pass filter and the minus 3 dB frequency. Need to zoom in around this 13 kilohertz, so that's a good sign. So we're going to go up to megahertz and maybe up from kilohertz, and minus 3 dB because the pass band is 0, 100% pass. So minus 3 dB would be around 15 kilohertz. So there we go. Made it work. All right, now we're going to do the same thing, but with a single stage RC low pass filter. Now, if we have an RC low pass filter using our capacitor, then because of the different behavior of the capacitor versus the inductor, this is going to be laid out a little bit differently. So we're not sure if this is the right resistance value. In fact, it would be kind of weird if it was, but we're just going to leave that as a resistor in there for now, and then we're going to figure out what the real value should be analytically. Anyway, this is the low pass filter with a capacitor. So we've got a capacitor here because at low frequencies this is infinite impedance, so the voltage divider is going to work in our favor, while at high frequencies it's going to be shorting out the output. So B, need to choose the R value for this circuit. And similar to the first time, we've got the transfer function just from a voltage divider, which is going to be ZC, so 1 over j omega c over 1 over j omega c plus R. And after simplifying, that's 1 over 1 plus j omega c times R. So this tells you that the magnitude of the transfer function is going to be equal to 1 over root 1 plus omega c r squared. So we need, so the minus 3 dB frequency is when omega rc is equal to plus or minus 1, and specifically we need it to be plus 1 to have a positive frequency, which means omega is equal to 1 over RC. Or in this case, we're going to be better served solving for R. R is equal to 1 over omega C, which is 1 over 2 pi f times C. And we can substitute in what we've got in this particular case. So 1 over 2 times 3.14159 times 15e3 times 1e minus 6 for 1 microfarad. And that means we need, to make this filter work, we need a resistor value of 10.6. Whoa. So it's just, yeah, that's quite the different resistor value from the RL circuit. 10.6 ohms. And let's double check that actually works in multisim. So we'll put 10.6 ohms there, and we'll get a different Bode plotter tool down here. You can stack as many of these as you like. I guess probably limited by RAM or something. Computer performance speed on the circuit. So as many of these as you like. So here's, yes, indeed, another low pass filter. We can go from go up to a megahertz and go from 1 kilohertz, and the filter does indeed look pretty similar to this other one, pretty much identical. So let's see if we've got our minus 3 dB frequency at 15K. Yep, pretty much. So it worked. We've got our low pass filter designed using a capacitor rather than an inductor. Okay, so the next part is a bit of a challenge exploration. We're going to cascade these two filters that we just came up with, which means we're going to make the output of the RL filter the input of the RC filter specifically. So that means that we're going to take all of, I don't really want that ground pin, so I'll get that out of the way. Let's just copy components here. We're going to take this thing, we're going to take this thing, and we're going to take our L there, and then the same R value that we've got. And then this is the output of the first filter. We're going to use that rather than the voltage supply as the input for the second filter. So we're going to build this filter circuit. And the idea is, okay, this first one was low pass filtering with a cutoff of 15K. And this second one was low pass filtering with a cutoff of 15K. So if you cascade them, then maybe you'll get an even better low pass filter with a cutoff of 15K. So let's analyze this circuit and see whether or not that works out. So this is the cascaded circuit. And okay, so first off, intuition about this, we are going to have this whole branch in parallel. So for this branch in parallel, we've got a resistor value here, and then it's in parallel with this impedance. At low frequencies, the capacitor is going to make this infinite impedance, so we're just going to have this thing being affected. But at high frequencies, the capacitor is going to be shorting this out, and the 10.6 in parallel with the 9425 is going to be quite a lot lower resistance. So it's not a perfect shorting it out, but it's pretty good. And so this part by itself is acting like a low pass filter in the voltage divider, and especially so when we've got the inductor up at the top. So this is only allowing the low frequencies to go through, but at high frequencies, it's stopping a lot of those from happening by making the top branch of the voltage divider a lot larger. So this is still a low pass filter, and it should end up being a second order low pass filter because we've got those two different effects that are acting to make it a low pass filter. So low pass filter should be second order. Let's see if that works. So for the transfer function, it's the same idea as the filters we were doing in the earlier problems, a little bit more involved than the ones, the simple single stage RC and RL low pass filters that we just did, but same idea. So we've got H is equal to Z bot over Z bot plus Z top, which would be for Z bot, we're going to have 9425 ohm in parallel with 10.6 ohm in series with 1 over j omega times 1 microfarad. That's our Z bot. And for Z top, we're going to have j omega times 0.1 henries. Okay, so this parallel impedance is equal to 1 over 9425 ohm plus 1 over 10.6 ohms minus 1 E6. Let's put a J in front. 1 E6 per farad divided by omega. So then we've got H. Let's get a little bit more space here, a little bit more real estate. H is equal to this thing is going to be a 1, and then this is another 1 there, and we're going to have, by inverting and multiplying, we have this thing multiplied by that. Okay. So we can clean this up a bit. We're going to have the inductor part going through, and there's that. So here's the entire filter part. So to see this a little bit more clearly, I think that we don't have to worry about this 9425 in the denominator because that's all real, but we might want to multiply all the terms by this in order to get rid of the fractions and fractions a bit. So why don't we do that? So we'll have that in the other term in the denominator. We'll have one of those in the numerator, and we'll have we'll have one of those multiplied by this thing. Okay, so then let's carry this thing through. So we've got one of those there and another one there, just multiplying it out. And then we can simplify. The minus j squared is going to be a plus, and the divided by omega and the multiplied by omega are going to cancel. And the 0.1 E6 is going to be 1 E5. Then maybe we want to collect all the imaginary terms together. And all the real terms together. So this one is a real term. We'll put that over there. And then we've got imaginary terms of plus j. And what are we going to have? We're going to have a minus 1e6 per farad per ohm. We're going to have a 10.6 ohms divided by 94.25, having factored out the j there. And we are going to have this thing. Okay. Now, to make this just a little bit more clear, you might want to maybe collect the omega times 0.1 into this term. So that'll be 0.1 henries times omega times 10.6 over 94.25 plus 1. And yeah, okay. So now we've got, let's just sort of double check that this is still low pass filtering. So if omega goes to 0, then this term dominates the numerator and the same term dominates the denominator. So we've got a that same thing limiting us to 1. And if omega goes to infinity, then we've got two things that are making it go, at least potentially two things that are making it go away. We've got this term disappearing, which was giving us a lot of gain. So we're ending up without that term. If we just look at the things that scale linearly, we've got a 10.6 over this 1e5 divided by 94.25 plus another 10.6. So that's a pretty extreme voltage divider that we were talking about there. And the other part is that we have this omega term that's left unattended in the denominator to explode as frequency goes towards infinity. So this is the other part of the low pass filter. Okay, so in order to find out what the 3 dB frequency is of this, we're going to have to look at taking the magnitude and simplifying it. So to find the 3 dB frequencies of this, we're going to be looking for where this has reduced, the magnitude of this rather, has reduced to 1 over root 2, because the gain at extremely low frequencies we worked out is equal to 1 because of that limit. When we go towards a higher frequency than that, we should be reducing to 1 over root 2, and let's see where that occurs. So we can say the magnitude of h is equal to this, sort of the ratio of the magnitudes in the numerators and the denominators. And in the numerator, we're going to have, and actually, first of all, I guess we could say that all of the units are working out. So ohms here, henries per farad. So henries per farad, let's think about that. If we were to multiply numerator and denominator by ohms, we've got like a farad ohms, which is a second. Then we've got henries per ohms, which is working out to, well, I mean, hold on, let's see. So we know that seconds is equal to henries per ohm. That's our time constant for inductor circuits. And then that's also equal to ohms times farads, which tells you that henries per farad should be equal to ohm squared. So that means that, yeah, we've got ohm squared per ohm here. So that's all gonna work out. So that's all just in ohms. And then this part, we've got henries multiplied by radians. And then we've got this 1 over farad times, so henries times rad per second, and 1 over farad times rad per second. If we take this whole thing and divide it by the ohms that we've got here, so we want to take that out of everything, that means we're going to end up dividing by ohms here, which is going to be seconds. And then same thing, this was henries, we're dividing by ohms, so that means seconds. And this was a 1 over farad. If we have another ohms that we end up with multiplied by that, then we get seconds. So everything is all good. We've got all the omegas multiplied by seconds to cancel out the units. Oh, wait a minute. What happened here? Let's just, oh yeah, okay, that's fine. So yeah, seconds, and then yeah, there we go. So then in terms of taking the magnitude, we're going to end up with, maybe I'll just write this as regular h. Don't want to do too many steps at once. So then magnitude of h should be equal to root 10.6 squared plus 1e6 over omega seconds squared. And then in the denominator, we're going to have a 10.6 plus 1e5 over 94.25 squared plus this whole thing squared. Great. And what we're doing here is looking for where this is equal to 1 over root 2. So at the 3 dB frequency, we need this thing is equal to 1 over root 2, because again, the gain in the passband was 1, so we just need this to be 1 over root 2 rather than something else over root 2. Okay, so now we can square both sides to simplify that a bit, and we're going to end up with 1 over 2 for that. Then we can sort of cross multiply, end up with a 2 times this stuff. And then over here, we're just going to have that left over on that side. Now, some terms are going to be potentially canceling and some terms are going to be sticking around. So we expect that there's only going to be one solution for all of this that makes sense. Now's a good time to jump to the calculator and see what we end up with. So we've got solving 2 times 10.6 squared plus 1e6 over, let's just call it w, all squared, is equal to 10.6 plus 1e5 over 94.25 squared plus w times 0.1 times 10.6 over 94.25. Just shout it out if you see me type something wrong. Minus 1e6 over w squared. Yeah, so let's give that a shot. And we expect to have only one viable answer. So we do have two imaginaries. That's good. And then we've got a negative and a positive. So that means that the answer for this is 4905. So if this is W, maybe W3dB is equal to 4908, then if we take this thing and divide by 2 times 3.14159, the 3 dB frequency is now different. So rather than the, it's actually quite a lot different. Rather than the 15K that we had from each filter individually, this says that together, these two filters are acting like a low pass with a cutoff of 781 if we haven't made any mistakes. So let's have a look at what Multisim says and check whether or not that's the case. So we'll need another Bode plotter tool, put our input there, and input there, and then the output just across the capacitor. And let's see what we get. Okay, so we need to go to a lower frequency than we had before. And interestingly, it's telling us that it sort of is dropping off to something that we can't really see here. Let's increase the top here up to 2 decibels and even higher. Yeah. So what's going on in this circuit is that we have some resonance effects at the lower end. So it's not only low pass filtering, but it's giving us gain of a pretty significant amount. This is going to a 23 decibel gain at this one resonant point there. Now the minus 3 dB frequency looks like it is actually around this 700 and so hertz. So if we kick down this from the 200 kilohertz and we put this one up, we can zoom in a little bit more clearly on that. Minus 3 dB is, looks like 779 or so, 781. Yep, okay. So minus 3 dB frequency is around what we calculated. And now, while we're here, let's look around at let's see if we can understand what's going on with this resonance effect. So it looks like something special is happening at about 500 hertz. And to see what's going on with that, we'll go over to the back to the analytical part. Now, there's a point where, because we have the L and the C acting in the circuit in the way that we are, we can zero out this. We can get some minimum for this magnitude, and that is going to end up with us in a situation where we've got 10.6 squared plus 1e6 over omega s, and then over here we've got 10.6 plus 1e5 over 9425 all squared. So the point where this actually cancels out should be, let's see, let's call this the resonance. W res looks like it's going to be, if you simplify this out, should be square root of 1e6 over 10.6 over 9425 plus 1. And that says that it's 999. And if we take this and divide by 2 times 3.14159, then we end up with a 159 hertz for that. Oh, you know, I forgot a 0.1 in there. That makes more sense. Okay, so it wasn't just this 10.6, it's this thing, but then we've got a 0.1 for that. Okay. All right, yeah, that's more like it. So 503. So 503 is our resonance. And actually, I guess we kind of knew that. We've been working with the same inductor and capacitor for a long time. So we've got our resonant frequency of 500 hertz as typically happens. Now, at that point, we've got, let's look at the rest of the stuff that we have for magnitude and see if it's bigger. So we've got 10.6 squared plus 1e6 over 503. Oh, no, we need omega over 3162 all squared in the numerator. And the denominator is this 10.6 plus 1e5 over 9425 all squared. So the numerator ends up being a fair bit bigger than the denominator in this case. So what we've got is a resonance effect. So the minus 3 dB frequency is the only real positive solution to this equation, which is at, we found out just to summarize some earlier points, 4909, and that is F equals 781 hertz. However, there's another point where the term from the complex part in the denominator cancels, which is at omega equals this 3162. So omega equals omega res. Rad per second. F is equal to 503 hertz. At that point, the amplitude is higher than the limit of the passband, or the limit of low frequency of 1. And the specifically, we found an amplitude ratio. Well, okay, hold on. I guess we have to substitute into the regular amplitude function. So we took this, the sum of this thing squared over this thing squared, but now we need to square root all of that. So if we take that thing divided by that thing, and then we take the square root of all of that, then we get 14.91. 14.91. In decibels, that would be 23.5. Now, if we go back to the multisim solution, hey, there's our 23.5 decibels at the peak there. And we might be able to get exactly to 23.5 if we zoom in around the 500 hertz. So 500, and let's go just a bit higher. How close can we get? 23.477. So pretty good. Pretty close to this 23.5 that we were expecting. Okay, so a couple of points. The cascaded low-pass filter, yes, still acts like a low-pass filter. Yes, has a sharper cutoff as you go to higher and higher frequencies. However, it's a little bit more complicated than you might have expected. We ended up with a resonance effect where we have more than one gain at certain frequencies inside the passband. It kind of goes up before it starts going down. It definitely doesn't have a cutoff frequency of 15 kilohertz anymore, and is perhaps cutting off some of the frequencies that we wanted to pass before. If we wanted to have an okay gain still at 1 kilohertz, then this doesn't really work like that. So although qualitatively you can take filters and that are two low pass filters and cascade them like this with passive filters and still get a low pass filter and a low pass filter that works as a second order filter, it certainly isn't true to say that the filter is just going to have the same cutoff frequency as the two individual filters, but then with a sharper roll off. That's not quite how it works. It's a little bit more complicated to design these two-stage filters than that. So the follow-up questions here, would it matter whether we put the RC or the RL filter first? Well, if we were to interchange all of the RC and RL stuff in here, well, that probably wouldn't change where this resonance part of it happens, because that ended up just being based on the omega is 1 over root LC. However, the rest of the circuit, so whether we're going to have a capacitor or inductor limiting term in the numerator, should be a bit different. And to get a quick answer for this, so we could go and redo the math and analyze it all in that different form, or we could just sort of copy and paste the whole thing down there and then swap out the inductor and the capacitor. And I guess we also need to actually swap the resistor values. So let's go ahead and do all of that. So here's our capacitor. There's the inductor. Whoops, nope, that's not the right connection. Up to the other side of the resistor. And we'll change this one to 10.6. And the other one to 9425. Okay, so now we have reversed the order of the stages in our low pass filter. Let's see how this one works. Okay, so things have changed from before. If we look from 10 kilohertz to from 50 hertz to 10 kilohertz, it looks like things. Oh, so did you notice what I did here? So by switching exactly the position of the capacitor and the inductor, I've actually converted this into a high pass filter with the same parameters as before. So before we get rid of this, why don't we just have a look at how that works? Do we still end up with a resonance type effect? It's sort of disappearing here. Kind of outside the range of what we are simulating. Interesting. There we go. I had to just rerun the simulation to get this. So let's go up higher than that. So interestingly, in this order, we don't see the same kind of resonance. We get a roll off in the other direction. That's for the high pass filter. All right, that's enough of that. Let's swap the stuff around to make it into a low pass. So what we need to do is maybe we'll first get rid of this Bode plotter tool so that's not in the way. And we need to move these components around a bit. So let's get rid of these wires. So we'll put this over there and put the inductor up at the top. And then we'll take the capacitor and put that down at the on the low branch of that divider, and the resistor up at the top. Okay. So there we go. Now it's a cascaded RC and RL low pass filter. Yeah. Okay. So we'll hook up our input and output. And see what we get. Okay, so going from 10 to 50, things are working out a little bit differently. And in this direction, actually, it looks like the 3 dB frequency is around 10K. So perhaps surprising, very different behavior in one cascade direction than the other. So this kind of sort of further explains how designing two-stage filters can be difficult. It's not nearly the same as designing one stage, designing each stage and then combining them, because the impedance of one filter is sort of affecting what's going on with the other filter, right? So the output of this one was affecting this voltage divider, and here we have the capacitor impedance is going to be affecting the voltage divider on this side. So the filter design in general, while you have the tools to analyze any of these filters, designing two-stage filters is a complicated topic and one that you'll return to more in your third year course. So that should give you a bit of an impression of what's going on, and hopefully a bit more understanding of some of the complications of designing these filter circuits. Hope you've enjoyed. Thanks for watching.